This is my narration of Lab 4, which focuses on temperature. So this is definitely going to bring in a lot of insights from your lecture in G107. So when you try to understand why does temperature vary across Earth's surface, there's many different reasons. First off, as we've learned before in previous labs, latitude plays a key role. Also, as we've also learned, altitude plays a key role. As you go up in elevation, temperature goes down, as we learned Lab 3 in the very first part. Also, other reasons why temperature varies is whether or not you're deep within a continent, and if you are, you're going to have bigger changes in your temperatures. Your highs are going to be higher, your lows are going to be lower, whereas if you're closer to a water body, your temperatures are going to be moderated. What that means is your temperatures won't get as high, but they also won't get as low. And so one of the things you'll notice is places along a water body will have temperatures that won't change much at all during the day or even throughout the year. For example, look at Key West, Florida, in which pretty much every day is somewhere in the 70s or 80s. It doesn't matter if it's winter, doesn't matter if it's summer. And a lot of that has to do with the fact that it's stuck in the middle of a large water body, the Gulf of Mexico. Further, other reasons why we see different temperatures is albedo, or essentially the color of the surface. And so albedo refers to darker surfaces, darker colors absorb and retain heat better, whereas lighter colored surfaces that have higher albedos have more reflectivity, and those lighter colors are going to then reflect that heat and thus not absorb it and not retain the heat as much as dark surfaces. And so essentially latitude, altitude, water and land heating differences, albedo, but also cloud cover plays a key role in understanding temperature differences. When we graph different phenomena in G108, we're going to use different graphs. Could be a line graph, could be a bar graph. We're going to use line graphs whenever we're trying to find a moment in time, a magnitude at a point in time. So temperature at a certain time, temperature, whether it be temperature in January, temperature at 2 in the morning, it's a specific moment in time. And so we're going to refer to this as continuous data. What that means is temperature doesn't just go from 48 degrees suddenly up to 52 degrees. It goes from 48 to 49 to 50 to 51 to 52. It's continuous. And so when we look at temperature especially, we're going to use line graphs. Whereas if it's stuff that can be actually quantified, stuff that can be put into a container, for example, rain, snow, can be put into a container, then we're going to use a bar graph. So bar graphs we're going to use to measure a particular period of time. So for a day, how much rain did we get on a certain day? Well, we'd use a bar graph to showcase that. How much rain did we get for a certain month? Well, we'd use a bar graph to showcase that. And so line graph versus bar graph is something we're going to have to make sure to separate and distinguish going forward. Parts 1 and 2 are going to ask you to create a climograph and then answer questions based on those climographs. And so what we have here is we have Indianapolis. So just using an example of Indianapolis. And so just to familiarize ourselves with the climograph, at the bottom we have the different months of the year. And one of the things you'll notice, you see D on there twice. And so December's on the left side, but it's also on the right side. So that's something to first off to get stuck in the head. Second, if we go over on the right-hand side, that's temperature in degrees Fahrenheit. So we have all the way up to 100 at the top right-hand corner and then all the way down to -40. And so what you're going to do is you're going to then plot temperatures for different months. And so in this example of Indianapolis, I've already done that. First off, what we note is if you look at where those dots are placed. For example, the dot for January is going to be right in the middle of that box. It's not going to be on a line. So the plot for January, which is just under, somewhere right around 28 degrees probably. So 28 degrees, you'll place a dot inside in the middle because it's an average temperature for the month. In the middle of that so-called area or region that's supposed to be for January. So then you see the January placed, and then we go to February, March, April, blah, 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 blah. And so what you'll do is you'll then place all the points on this graph, and then you'll connect them using a smooth line. So you'll connect the dots and try to create kind of a curved line that connects all the points. Further, one of the things you have to note is what to do with December. So December is actually, there's two dots that show December, but both of those dots are going to be on the solid black line on either the left-hand side of the graph or on the right-hand side of the graph. And so you'll see for December, which is 30 degrees, is the average temperature in December in Indianapolis. You'll see it on the left-hand side on that solid dark black line, but also on the right-hand side. Essentially what it is, December is cut in half. It's on both sides of the climograph. And so your climographs, now they might not look exactly like this, but they should look like this in terms of the general makeup, with the dots in the middle of the particular month that the data is for, but also with December being shown both on the left-hand side and the right-hand side. For part 1, keep in mind the title of it, Altitude Effects on Temperature. For question 4, it's going to ask you to use an analemma and then draw an arrow that showcases when the subsolar point is overhead at our location. And so what's our location? Well, if we look at the part 1, La Paz, Bolivia, 16 degrees south. Concepcion, Bolivia, 16 degrees south. And so you're going to use the analemma to find out when, at 16 degrees south, the subsolar point is directly overhead. And it's going to happen at 2 different times during the year. And so you'll find out that day, and then what I want you to do is go up to your climographs for both La Paz and Concepcion and draw an arrow pointing that says this is the time, this is the month, and also the time of the month in which the subsolar point is directly overhead. For part 2, keep in mind the title, Marine and Continental Effects on Temperature. Here's part 3, albedo effects on temperature. Here's the missing data, so go ahead and fill this in and then answer the questions subsequently. This is from a day in September of 2013 in which the high temperature for that afternoon was 90 degrees, and so that was the ambient air temperature, as they would say. In part 4, we're introduced to isoline maps. The idea here is these different colors are associated with different precipitation totals in this particular example. So over on the right-hand side, we've got different amounts. So we can see that places that are blue have more rain than places that are orange and brown in color. So we can see that over on the Pacific Northwest, but also in the American Southeast, you see a lot of blue. That means they get a little bit more rain than the other places. And so you can definitely see a west to east pattern in which it's, for the most part, drier in the west and wetter in the east. So we'll go ahead and look at our first example to help try to understand how to answer these questions. And so for A, we can see it's somewhere in the orange, that light orange category. That light orange category means it's going to be somewhere from 12 to 20 in terms of its value. So if you just put a number anywhere between 12 and 20 in terms of number of inches in terms of precipitation, that would be acceptable because it's in the orange. But if we can probably make a little bit better of an inference, a little better response, because it's closer to the green. So that A is closer to the green, which is the 20 to 30 category. So I would say that's probably somewhere between 15 and 20 degrees is the value for A. So that's just a kind of an introduction to these isoline maps. So any response between 15 and 20 would be fine for A. Now, instead of looking at precipitation, let's look at temperature. And these are called isotherms. And so the different colors are represented by different temperatures at the top. So if we go ahead and just use an example, let's go ahead and look at A. So A, we can see it's in the green, the kind of the light green color. So it's going to be somewhere between 70 and 80. Now we have to kind of have a more precise temperature reading from that. And so we can see A is very, very close to the blue, the turquoise, which is in the 60s. So I would say an educated guess for the temperature of A would probably be 70 degrees, 71 degrees, not much above 70. Here are the 4 rules for drawing isotherm lines. First off, every point on an isotherm is the same value. Secondly, each isotherm separates points of either higher or lower temperatures. Third, isotherms never cross, and they never ever split. And finally, isotherms, they always close to form a circle or extend beyond the mapped area or extend to the edge of the page. In this particular lab, you're going to have an example of where you're going to have irregular patterns, but also where you're going to have ones that are where they extend beyond the mapped area. So you're going to see both of these examples. So as you work through the number 14 and draw out your own isotherms, pay attention to these rules. Come back to these. And so instead of just kind of quitting or saying, man, my professor sucks, he doesn't teach me anything, focus in on these key rules and apply them to the question. Now I'm going to walk you through how to draw isotherms using our example. So here we at the top. Let's go ahead and read the instructions. First off, using pencils with erasers. So I highly suggest using pencils to do this because you will make mistakes. So drawing isotherms below using an interval of 5 degrees beginning at 0 degrees Fahrenheit. Then use color pencils to shade the area between the isotherms, and that's all stuff you can do later on. First off, we got to draw the lines. So which lines do we draw? So we look at the instructions and it says we begin at 0. So that's going to be our first line we're going to draw, 0 degrees. And we're going to draw every 5 degrees. And so on the right hand side, 0, 5, 10, 15, 20, 25 are the 6 different lines that we're going to draw isotherms for because we're using an interval of 5. Notice we don't do 30 because the highest number anywhere on this map, the highest measurement is 29. So because of that, we will never have, in this case, we won't have 30 being drawn because we don't get that high. The highest we get is 25. Now, I'm getting ahead of myself, but at the bottom is questions 15 and 16. 15, the temperature range is just the highest value minus the lowest value. For 16, the mean temperature, this is kind of, stupid. This is going to be tough, but just add up all the numbers and then divide by the number of numbers that there are. So get us off the right foot, go ahead, and this is the line showcasing 0, and it satisfies all the rules of how to draw isotherms. So first off, all points have to be the same value, and so because we're drawing the 0 line, it makes sense we're going to go through the 0 point. Other rules are that they have to either form a circle or go to the edge of the page. So in this case, the simplest way is just do a circle. For the 5 degree line, we can draw it here, and once again we go to either the edge of the page or we draw a circle. And so in this case we went to the edge of the page, and so the 5 line. Notice that all points on one side are below 5, 4, 1, 3, 4, and 0. All points on the other side of the line are above 5, 6, 6, 8, 8, 7, 10, blah, blah, blah. And so this once again satisfies one of our rules from the 4 rules of isotherms. Next up, I went ahead and drew the 10 and the 15. And so once again, you note that the 15 point is there, and so that 15 line should go right through the one observation of 15 degrees Fahrenheit. And so then we can kind of see some patterns. And so when you draw your isotherm map, you see at the top part of the map, the 3 and the 22. So that means between the 3 and the 22, you're going to have to squeeze the 5, the 10, the 15, and the 20 between those 2 points. And so that's kind of how you have to plan things out. When you draw these isotherms, you have to start looking at and observing the data values as you start to interpolate or interpret the data. Here we have the 20 line. And then for the 25 line, you have, once again, these are going to vary from person to person, so you have 2 different options. You could make a circle around those values that are above 25. Or you can have that line extend from one edge to the other edge. So there you go. And for part 5, you'll be plotting actual real isotherms on a real map with real observations. And so on the left-hand side, at the bottom of that page, you'll see the mean January temperatures. I went ahead and I've done that for you. On the right-hand side is the mean July temperatures. So both of those you'll then use to answer the questions that remain in part 5. So once again, that's where you incorporate G107 insights into your analysis, into your responses. For part 6, we look at wind chill and heat index. And just to briefly explain wind chill. So why is it important? We got to think about our body as far as it's radiating heat. So it's radiating long wave radiation. It's radiating thermal energy. It's emitting heat from our internal organs outward. And so what happens with wind chill is wind especially as wind becomes even faster, accelerates the removal of that heat from our body and from our skin. And so that area just above our skin. And so essentially, when we think about wind chill, it accelerates the removal of heat from our bodies, which is why in the wintertime, it's of chief concern. In terms of heat index, what it is when we see high temperatures along with high humidity levels, essentially what it is your body, it sweats and it perspires to try to create evaporation. And so evaporation on our skin, essentially water goes from being a liquid to a gas. And so essentially water on our skin evaporates. And so because of that, that's why we perspire. We naturally are creating evaporation, which evaporation promotes cooling at the surface. That's why when you jump in the pool in the middle of the summer, even if it's 180 degrees outside, you get out, you get the chills because the water on your skin is evaporating. It's going from being a liquid to a gas. And so when we think about heat index, why when we have more humidity in the air, essentially more water vapor in the air, our bodies have to work even harder to keep itself cool. And so heat index, we think about the key reasons as far as why relative humidity influences temperature and why that has to do anything with our own bodies is the fact our bodies naturally perspire, but when it's so humid out, when the humidity of the air is so high, it has to work even harder to keep itself cool. To showcase tight weave and loose weave, I've showcased that here using these diagrams. And so on the left-hand side, we can think of that as being loose weave. So it's like wearing sweatpants. Where on the right-hand side is a very tightly woven fabric. So that's how I can showcase this. And so if you think about which one of these has more yellow exposed, definitely one on the left is going to have more yellow exposed and some more of that underlying surface area exposed. So when we think about wind chill, we can layer up, but if we layer up with a bunch of sweatpants and a bunch of loosely woven fabric, it's really going to protect us as much as like a windbreaker. Something that's very, very tightly woven, it's going to prevent that wind from removing the heat from our bodies and from the skin layer. The wind chill and heat index charts are very, very simple to read. So let's go ahead and go through an example here. So we have wind speed of 35 miles per hour, air temperature of 0 degrees Fahrenheit. So we go over here, you look at 35 miles per hour. So you find that at the top, and so it's going to be somewhere in that particular column, the 35 column. And then we have an air temperature of 0, so we go down to 0, and that should be the negative 27 degree, make sure you label, Fahrenheit would be the wind chill. And so at 35 mile per hour wind at 0 degrees is going to be a negative 27 degree Fahrenheit wind chill. Now using the heat index table, go ahead and infer that. And so we have a relative humidity of 90%. So we see that it's over at the top, the 90 up there at the top. And so then we have a air temperature of 86 degrees Fahrenheit, and so kind of like battleship, so 90, where they meet, 105 degrees Fahrenheit would be the heat index on a day in which the relative humidity is 90% and the air temperature is 86 degrees. And so all the other questions you should be able to answer in some way, shape, or form from your G107 insights. And I highly encourage you. What they say about you guys, young people, is that you aren't able to think creatively. You aren't able to think on your own. So you're great at memorizing things, but you aren't able as far as answering the why question. I disagree. I think you can. So when you answer the other questions, the knee jerk is, well, I'm just going to ask the professor. I'm just going to come and meet him, meet him early. Try to answer the questions as best you can. So do not come to me with questions in which I can tell you haven't done any research, you haven't done any deep thought. But all of this should be pretty self-explanatory, and I hope you've done well.